thank you. Okay. Step. So I'm going to copy step 3 to step 4 and work on step 4. Okay, so is everyone okay with the copying? If you need more time, just raise your hand. Okay, so now we will use the offset that we calculated earlier to calculate all of the multiple expansions, and then all the multiple expansions here, and then the local expansions here, and finally the UI here. But we can't check the answer yet because we're missing the M2L component that needs the neighbor finding, and also the P2P component that needs the neighbor finding. So yeah, why don't we do the neighbor finding first, because then we can do all the kernels in one pass. So the next task, let's do this one. So the task is, given a number 26, we will use the get ix function that we have to calculate this, and then calculate its neighbors by looping, and then calculate the index of the neighbors by using getIndex. Okay, so let's do this calculation inside step 4. Okay, so we can do it. We can just do it here. So let's say we had number 26. So there's a function we have called getIx. This one here. We're going to use getIx, and so for an index 26, so we're going to just put here 26 because we're going to calculate for 26, and then we will use ix here and see what we get. Let's just print. It's very easy. Just call get ix with 26 and ix, and then printf the two numbers of ix. So let's do ix0 and ix1. Okay, everyone has written this. Oh no. Okay, is this correct? 3, 4. Yeah, good. Okay, so we did the first part now. So neighbor finding, find from 26 we get 3, 4. From get ix we input 26, and the ix we returned 3, 4. Okay, that's the first part. And so now let's create a loop. Let's make a loop from so let's say we have ix, iy, and iz again, like yesterday, except ix goes from -1 to 1. And the same for the other two. So iy goes from -1 to 1. Iz goes from, oh no iz. Iy, and so we have the loop in two directions. And let's print ix 0 plus ix and ix1 plus iy, like this. Then this should print those values that we need. Yes? So now it's printing 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, 3, 5, 4, 3, 4, 4, 4, 5. This is the values that we wanted in this here. 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, 3, 5, 4, 3, 4, 4, 4, 5. We have these values showing okay. Well, actually, maybe I should have put the while loop on the outside, because then the order would be, well, it's fine, I guess. And now, from these two values, we want to calculate the index. So okay, so why don't we define a new ix? So ix, we use plus, with the shifted value, we have ix2 with the shifted value, like this. And then we call get index let's see, index is already being used. Maybe we can just use IC here for now. IX, what was the other value? Index, IX, and level is 3. Okay, so if we print the IX2 values with the new IC value, we should get the two-dimensional index. So like let's make it look like a 2D index becoming a one-dimensional index. If we print like this, then when we print when we print oh, something's wrong. That's right. Get index changes. I need to put 2 here. Because get index overrides the values, so we can't use whatever went into get index doesn't come out correctly. Okay. So let's compare the results to the values here. Okay, so now you can see the code and the numbers and the output and this table. So 2, 3 is 13. We have 24, 25, 13, 24, 25, 15, 26, 27, 15, 26, 27, 37, 48, and 49, 37, 48, and 49. So we have these values. So I'm just outputting like with the parentheses and the equal sign so that it looks like I'm calculating from the 2D index, the 1D index. But all we did was just get the index here and just have a double loop in the two directions. So the reason why it's looping over 2, 3, 2, 4, 2, 5, it's looping up first is because the y loop is on the inside and the inside loop is executed first, and that's why it's going in the y direction first. If I wanted this to go in this way first, I just need to put iy in the first loop and ix in the next loop. But that's the only reason why it's going this way first. But anyway, it's showing all the neighbors. So, okay, now we have the neighbor calculation ready. So now we can actually start doing all the kernels, potentially. Okay, so now let's do okay, so we can leave this code here and then go on to do the P2M kernel after this section. So the first thing we want to do for P2M is to loop over. So this is the inside loop going over all the multiples, but outside we need to have a loop that's going over all the boxes, all the cells. And for each cell we have an offset start and end. And also we need to be careful because this offset thing, oh yeah, so the offset actually needs to be continuous for this to work. So I guess I made one change in the previous code, if you remember. This offset here, I changed to index I, but no, this actually needs to be ID because otherwise the method I'm showing here with going from 0 to 1 doesn't work if this is not ID. So change this back to ID because this needs to be ID. And then what we will do is loop over. We know ID is the number of cells, so maybe we should change the name so it better represents what it's doing. So ID is actually, this is the number of cells. Okay, so now we are basically calculating the number of cells and their offsets. And so we need to have, so offset 0 is obviously 0. And then I think we need to have one last offset defined for the final loop to work. So say that you're at the last box and we need this offset, end offset. So we need to define another offset for the final ending offset, which is basically n. So offset n cells equals n. This because the final offset should, the beginning offset is some number that we don't know. But the end one means this is the end of all the particles, which means it's like n. It's always n, the final number. Okay, so now we know how to loop, right? Because we just need to loop from 0 to n cells, because we know how many cells there are. Now we've counted them. So we know, but this is just at the bottom of the tree. So we know there are n cells at the bottom of the tree because of this calculation we did here. We don't know how many are at the higher levels of the tree, but so we know that there are this many cells. Okay, so now we are looping over all the cells, and here is where we do this thing. And instead of using 0 and 1 here, this becomes like I and I plus 1. Of course, it starts from 0 and 1 when you're looking at the first cell. But then you look at all the cells and then you add to the multiple. But then we need to define another array here. We need to define this one, the multiple expansion for each cell. So this number represents the multiple expansion, or you can think of the sum of the charges at the center of each cell. So there's only one number per cell. We know that there are n cells at the bottom of the tree, but we have this value not just at the bottom level of the tree, but at every level of the tree. So this array needs to have the size of the total number of cells in the tree. So how do we determine that? If we know how deep the level is, then we know how many at most cells there are. So basically we have level 3, right? We define somewhere that level is already 3. I think it's defined, here. No, but this is defined, this should be defined like outside so that, okay, so now we've defined level 3. Let's define it at the beginning so it's very clear what we are doing. So let's define that we are calculating at level 3 with n equals 1000 for this calculation. These things we can change. So when we change this to like 10,000, we can change the level to 4, for example. But we only need to change at the beginning. And then, since we know the level, we can calculate how many points we have. So we just need to loop over the levels. I think we defined, so let's just loop over the levels. And then we add the number of so the maximum number of cells you can have, we can know, right? We can have at each level, we have, since this is a quad tree, it's 4 to the power of I, yes? So I can print how many that is. So let's try to print the level. So at each level, how much is the power 4 to the ith? Okay, and let's just neglect this thing for a moment. Okay. Oh. Okay, so something is not working, so I'm going to do a alternative. Yeah, okay, so now we see, so at level 0 we have 1 cell. At level 2, at level 1 we have 4 cells, and at level 2 we have 16 cells. So if we have level 3, which I think I need to do like a equal here so that it shows level 3. Yeah, so 64. And now in the whole tree we have to sum all of this. So max cells is the sum of all of these. Okay, so max cells has reached 85 in this calculation. For a level 3 quad tree, we have 85 cells in total, at most. Some might be empty, but we could have at most 85. This is the sum of 1 plus 4 plus 16 plus 64. So this is size of the array which we will use for the multiple expansion. Okay, so we did all this calculation for one reason. We wanted to have define the array called multiple, which we will make size max cells. Okay, some compilers may not like it if you do this. I think you need to define this in dynamic memory allocation size of double. Okay, so this creates an array of called multiple of size max cells, which we have determined to be 85 up here. So we have 85. This changes when you change the level of the tree, and only when you change the level of the tree. So say that you change to level 4, and then you will have 256 more cells. So let's calculate the first P2M kernel here. So we are now looping over all the cells at the bottom level, and inside that loop we want to loop over, so the offset of the ith cell to the offset of the ith cell plus 1 is, so these are all the charges we want to sum, and the multiple that we are looking at is the ith. Is it the ith? And then we just use, is it Q? Yeah, Q, right? QJ. We haven't initialized yet, and also I'm not sure if this should be I. I think there should be like a level offset here, because maybe we want to start numbering the multiple to be at level 0 to be 0, and then number them from up to down, and so the bottom level should start at 21, right? Because in the upper levels, you already have 21 cells, and you're basically here calculating the multiple at the bottom level. It depends on how you number them. You can number them bottom up, meaning that the bottom level starts, and then you add the next level to that, and then as you go up, if the index has bigger numbers, you can number like that. But I think it's more intuitive to number from top to down, because as the tree gets deeper, you'll have bigger numbers. I think that's more easier to comprehend. So let's add this number, this sort of level-wise offset to the I here. And in this case, we know that it's 21. But so where that number comes from is, let's see. So we need to have the level offset, which can be calculated in the same way as the max cells. Level offset. So we have 3 levels. So the size should be 4. Level offset for level 0 is always 0. And as we calculate max cells, the level offset is actually this number that we are adding. Or no, it's actually the max cells offset for level I equals I plus 1. So I plus 1 equals the max cells. And then we just add level offset. And this is at the bottom level.